I'm sitting on my floor, and today we're going to be determining the importance of eccentricity in the survival of planets in close binary systems. Most models of planet formation are structured around a single star host, though observations show that more than half of Sun-like stars evolve with one or more stellar companions. I'm going to attempt to demonstrate now the two primary models that we have for star formation in binary star systems, and I will be doing that with an experiment that I'm trying for the first time in real time with egg. This is our molecular cloud today. So our first method is core fragmentation. Due to the properties of the molecular cloud, such as density fluctuations, we form two protostars and two disks. Systems formed by core fragmentation tend to form binaries that are much larger, and oftentimes the protoplanetary disks do not affect one another. Our second model is called disk fragmentation, and this produces the short system binary systems that my project is going to be looking at. If the disk is rotating too fast, gravitational instabilities can cause it to separate, and a second protostar can be turned on. Wow, what an insightful and incredibly successful experiment, something that we're going to try to reproduce here today. While we've observed many planet hosts with binary companions, when we start to look at demographics, we see that close binary systems are far less likely to host planets. Krauss et al. 2016 surveyed a number of candidate planet hosts, looking for binary companions at less than 50 AU. Where they expected to find 58 binary companions, they found only 23. This makes sense when we look at our model of disk fragmentation, which is a highly dynamically active environment and is very hostile for forming planets. What's interesting about these results is not as much that there's a sharp decline in close binary system planet hosts, but that some of them make it. This begs the question, why do some of them make it? We look at two possible explanations that come up: mutual inclination and low eccentricity. For my project, I propose an extended astrometric monitoring campaign that explores the correlation between the survival of planets in close binary systems and the eccentricity of their orbits. This will look at orbits with separations of less than 50 AU. My target list will consist of the 23 identified Kepler objects of interest found in Krauss et al. 2016. I'm doing this because these are systems with separations less than 50 AU that we know have planets. The primary instrument in this project will be the Gemini North Telescope. The first step will be using their Altair adaptive optics system. Using the adaptive optics imaging, we'll be able to determine the separation of the two stars at the time of observation. The next step involves using the Maroon X high-resolution spectrograph, also at Gemini North. This will be an extended radial velocity observing campaign, approximately 3 to 5 years in length. By comparing expected orbital speeds from their initial separations and their radial velocity measurements, we can determine eccentricity. Finally, what we're looking for are any trends in the eccentricities of the orbits of these systems. The current expectation is that low eccentricity binary orbits may be a safeguard against planet destruction. If low eccentricities seem consistent, it would be a great indication that this question should be probed further and that more observations should be done to support it. If they trend higher, then a similar path to further observation should be done. It's also possible that no trend will appear. This doesn't mean that eccentricity should be rolled out as a factor in the survival of these systems. It just means it may be one of many variables. This work hopes to further our understanding of planet formation in binary systems. There's still a lot more observational work that needs to be done, and there are many more questions to ask about these systems, in particular if mutual inclination plays a large part in the survival of these systems. Thank you so much for watching. I have been sitting on my ankles this whole time, and this is NPR.